Welcome to this explainer. Today, we're going to bridge the micro-level mechanics of C++ initializer lists with the macro-level architecture of inheritance. Ultimately, this is all about helping you write incredibly robust, efficient code. If you want to understand not just how these C++ features work, but exactly why they were designed this way in the first place, well, you are in the right place. Let's get to it. Okay, so here's our highly structured roadmap to level up your C++ toolkit, perfect for any upcoming exams or assignments. We'll quickly run through initializer list syntax, dive into the 5 mandatory use cases, compare is-a versus has-a relationships, discuss why we actually need inheritance, map out the types of inheritance, and finally wrap up with syntax and visibility rules. All right, let's start our journey right at the micro level. Section 1, initializer list syntax, the foundation. Simply put, an initializer list is a specific mechanism used to initialize the data members of a class. The syntax is pretty unique. It's tied to a constructor and written as a comma-separated list of members sitting right after a colon. Basically, it allows us to initialize data members directly the moment an object is created, literally before the actual code block of the constructor even begins to run. You'll notice the colon right before the x of I, j part. That is exactly where the magic happens. Those variables get initialized before the constructor body ever executes. Now, in this specific case, the initializer list is optional. You definitely could just assign x equals I and y equals j inside the constructor's curly braces. But as you'll see, sometimes using this list isn't just a nice option, it's absolutely mandatory. And that brings us to section 2. 5 mandatory use cases where standard initialization just totally fails. Pay close attention here, guys, because this is classic exam material. Here's the big picture of the 5 specific scenarios we're going to tackle. Think of them as mini puzzles where standard variable assignment just won't compile. You literally have to use an initializer list for 1. Non-static const data members, 2. Member objects that don't have a default constructor, 3. Reference members, 4. When your parameter names match your data members, and 5. Base class members. Let's break some of these down. First up, if you have a constant variable, like const int t, you fundamentally cannot assign it a value inside the constructor body. It's a constant, right? It has to be initialized the exact split second it gets created. So you must use the initializer list, which looks like colon t of a, to give it its very first and only value. And you know what? The exact same logic applies to references. If your class contains a reference variable like int and t, C++ strict rules dictate it has to be bound to something immediately upon creation. You can't just declare an empty reference and assign it later on. This strictly requires our handy comma-separated initializer list. Now, our 4th scenario is essentially a namespace collision. If your constructor's parameter name is identical to your class data member, for instance, you're passing an int I to initialize a class member that is also named I, the compiler gets completely confused. To fix this, you must use either the this pointer to point directly to the object's member, or, what's vastly preferred, use the cleaner initializer list written as I equal I. It resolves the naming conflict perfectly. And this 5th point acts as a brilliant bridge to our next major topic. When you're dealing with inheritance, calling a parameterized constructor of a base class can only be done using an initializer list. So when a derived class called B needs to call the base class A's constructor using $ax, well, that is literally the only valid way to pass arguments up the chain. Which leads us nicely into section 3, is-a versus has-a relationships, building macro architecture. Whenever you're building software, the 2 most common ways to relate classes are through composition and inheritance. Composition is a has-it relationship. Think of an organization that has an employee. The organization holds the employee as a distinct part of itself. On the flip side, inheritance is an is-a relationship. An employee is a person. And because an employee is inherently a person, they logically possess all the traits of a person, like a first name, a last name, and ID, plus some extra attributes specific to their job, like a salary. Moving to section 4, why we need inheritance, the evolution of code. So why do we actually need this feature? Imagine you've been hired to write a brand new software system. You start with a basic calculator class, featuring just simple addition and subtraction methods. It works perfectly. Everyone is happy. But a few months down the line, a client comes back and says they want advanced features, like multiplication and division. Now you're facing a dilemma. You could open up the original calculator class and edit it, but you risk breaking perfectly functioning, already tested code. Or you could write a brand new advanced calculator class entirely from scratch that includes all 4 operations. But ask yourself, do we really want to implement the exact same addition and subtraction features over and over again? Doing that violates one of the core principles of programming, keeping your code dry, which stands for don't repeat yourself. So, do we rewrite it? Absolutely not. Instead, we use inheritance. By declaring class Advanced Calculator, public basic calculator, our advanced calculator seamlessly inherits all the tested working behaviors of the basic one. We literally just have to write the new methods for multiplication and division. That is the true superpower of inheritance, creating new classes from existing ones, safely enhancing functionality without touching or duplicating the original code. All right, Section 5, Types of Inheritance, Simple, Multiple, and Multilevel. Let's look at the shapes this can take.
A derived child class can be built on a single base superclass. We call this single or simple inheritance, like inheriting a specific circle class directly from a broader shape class. Alternatively, C++ is pretty cool because it allows for multiple inheritance, where a subclass inherits from more than one base class at the very same time. Just imagine a son class inheriting traits from both a mother class and a father class simultaneously. You can even string them together into multi-level inheritance, passing traits from grandfather down to father and then to son.
Finally, Section 6, Syntax and Visibility Rules. We definitely need to talk about avoiding some common traps here. The general syntax is fairly straightforward, but it's very exact. After declaring your class and its name, you drop in a colon, followed by a member access specifier that's going to be public, protected, or private, and then the base class name you're inheriting from. But here is something crucial to understand. The private members of a base class are always entirely inaccessible directly from the derived class, regardless of which specifier you use here. But here is a massive exam alert regarding that access specifier itself. What happens if you just forget to write public, protected, or private? Well, as our source material warns, when we omit the visibility specifier, the compiler assumes that we're going to apply a private inheritance. That means all the public components of your superclass suddenly turn into lockdown private access within your subclass. Let's actually see that trap in action. If you define class, sub, super, completely omitting the word public before super, it immediately defaults to private inheritance. The very second you try to compile this code and call a method like object.put100 in your main function, you're going to get compilation errors shouting that the methods are inaccessible. So please, always declare your access specifiers. Okay, let's recap the vital takeaways you should definitely be screenshotting for your notes right now. First, memorize those mandatory initializer list scenarios, especially for constants, references, and initializing base constructors. Second, keep in mind that inheritance represents an is-a relationship, whereas composition is a has-a relationship. Third, remember the main goal of inheritance is software reusability. Use it so you don't repeat code. And lastly, always declare your access specifier in your syntax to avoid accidentally defaulting to private inheritance. Ultimately, the crucial point here is mastering these structural tools so you can become a true software architect, not just a coder. Think deeply about the concepts we've covered today, from the micro-level initialization of tiny variables all the way up to building sprawling family trees of classes. I'll leave you with this final thought. If you were building a massive software simulation tomorrow, maybe a huge video game with vehicles that act as both boats and planes, where might multiple inheritance save you hundreds of lines of code? Keep building, keep exploring, and I will catch you in the next explainer.